and before we get to the main portion of this video, I wanted to clarify a couple things that I didn't do super well the first time I made this video. So I'm just going to add this quick bit to the beginning here before we get to the main part of the notes. This part of the notes is me talking about two special right triangles, in particular what we call the isosceles right triangle and a 30-60-90 triangle. Those are the two triangles that you see on your screen. This first one here on the left is your isosceles right triangle. Because of that name, it actually tells us everything we know. It is a right triangle because it has our 90-degree angle, and isosceles means that my two sides that are making that 90-degree angle, what we refer to as the legs of the triangle, are the same. Just a quick refresher on right triangles, the legs are the two sides that make the 90. The opposite side is what we call the hypotenuse. Okay, we'll use those terms all throughout the notes today as well. So real quick here, because I know these two sides are equal, this is an isosceles triangle. We know that in an isosceles triangle, my two adjacent angles here are going to be the same, what we call their base angles. Because I've already used 90 of my 180 degrees in a triangle, I know these two other angles here need to add up to be 90, but they're each half of that 90, so they're each 45 degrees. Okay, in the video you're about to watch, I go into that, but I don't do a very good job of explaining where it comes from, so I wanted to explain that real quick. The other thing I want to explain is this 30-60-90. The name 30-60-90 is referring to the angles. So we have a side that's, or an angle that's 30 degrees, an angle that's 60 degrees, and our 90 degree to make it a right triangle. With this one, it's really important to talk about the size of the legs. So we have two different size legs here. We have what we usually refer to as a shorter leg and a longer leg. The longer leg is not the longest side. The longest side is still the hypotenuse because that's across from the 90, but we refer to this as the longer leg because it's bigger than our short leg. Okay, hopefully that clarifies some of this, and we'll go ahead and get started into our video.
Good morning, everyone. Today we are going to be talking about section 13.5, which is our special right triangles. This is kind of our first real section of trig, which means we're working with triangles. We got to work with kind of some exact values, trying to estimate some stuff, especially dealing with angles and side lengths. So we're going to work with two triangles today. So we're going to first talk about those two triangles. We have an isosceles right triangle and then a 30-60-90 triangle. So we're going to start with our isosceles right triangle. So if I start with this isosceles right triangle, should look something close to that, where our two legs here that form the 90-degree angle are roughly the same length. Okay, they're exactly the same in reality, but drawing them, they should be close. Okay, and so we're going to start by calling these two sides x. So I don't know exactly what they are, but I know they're the same, so I'm going to call them x. Now what my goal is going to be is to find this third side, which for now I'm going to call c. We're going to figure out what it has to be. Okay? So to figure out what it has to be, we can go back to stuff we already know, which is Pythag. So we'll work backwards here a little bit. So I'm going to start with my two x's. I'm going to square them both and add them together. That's going to have to be c squared. So if I look, I actually have two of those x squared. So we're going to consider this to be 2x squared is equal to c squared. And in order to get c by itself, I need to take a square root. Okay? If I do that, my square root and my square cancel on my c, so I'm left with just c now. But now I have to worry about this square root. So the square root of 2x squared. So the square root of x squared is going to cancel out the 2 for the exponent, but I still have this square root of 2 here. So I know I'm going to get just an x, and that's now going to be outside of the square root. So I'm going to put that on the front. But I'm still left with the square root of 2, and there's not really anything to do there as far as simplifying. You can find what the square root of 2 is, but it's a really nasty decimal, and we'd rather just keep it as the square root of 2. So this is the thing that we're going to actually use for c. So we're going to say that c here is equal to x square root of 2. And I know that's a little clunky to work with. It doesn't look very nice. But as we start to move forward, you'll get used to seeing that and see that it's actually not that bad, especially once we know what x is. It makes it pretty easy. So let's talk about our other triangle. We got our 30-60-90 triangle, which if I draw that out here, we get one side that's quite a bit longer than the other side. And that smallest angle is going to be our 30 degrees. Next biggest is going to be our 60, and then of course our right angle, our 90. Okay. Now this triangle is actually part of a bigger triangle. This actually comes from an equilateral triangle. So if we remember equilateral, they're all the same. And really what we've done with that equilateral is we've split it right down the middle to form that 90-degree angle. Okay. Because we've done that, we can consider these outside pieces to all be the same. And this bottom piece here, which is going to be the bottom piece of the triangle I have, is going to be half of that, because it's really splitting this third side in half, if I think about that, going back to the equilateral. So I don't really like to work with decimals or fractions. So instead of saying that this side is half of the big side, I'm going to say that the big side is twice the smaller side, which is really the same relationship. It's just going the other direction. So I'm going to call my small side x, and then my hypotenuse, my biggest side, is going to be 2x. And using that, I can now work to find this third side. For now, I'm going to call it a, so I have something to work towards. But again, we can use Pythag to work back to this. So this one's a little bit trickier because I'm going to have a squared plus my x squared has to equal my hypotenuse, which is the 2x squared. And I need to square that whole thing. So I'm going to go ahead and put it in parentheses. Now I actually want to simplify this first. This is 2x times 2x. So I know I'm going to get an x squared, but the 2 times 2 actually gives me a 4 as well. So that's a little bit tricky. That's something you might miss if you're going too fast here. Okay? And so then we have a squared plus x squared is equal to 4x squared. Okay? And now I can try and get the 4x squared by itself, so I'm going to subtract, or sorry, the a squared by itself, so I'm going to subtract the x squared from both sides. When I do that, I get a squared is equal to, oops, sorry, ignore that. This is going to be a 3x squared because I'm taking one of those x squareds away. Now I can take my square root to get a by itself, and I get a is equal to, and this is going to be really similar to what we had over here with the 2x squared. I can square root the x squared to get me just an x, but that square root of 3 is going to be left over, and there's not really anything I can do with it. So I'm going to call this x square root of 3. Okay? Now the nice thing here is because I have all of these x's in here, if I have a side of one of these two triangles, and I can try and solve for the other ones just by knowing what x is. So if I take it and kind of set it equal to whatever part of this triangle I have, I can really figure things out pretty quickly. Okay? So let's look at our actual theorems here. So our theorems here in our vocabulary section are really just taking these two triangles and they're putting it in words. Okay? So for isosceles right triangle, it says that if I have an isosceles right triangle, isosceles right triangle with legs of length x, okay, so each of those side lengths of the legs are x, that implies sorry, it's not in there. The hypotenuse is x square root of 2, which is really the same thing we have up here. If my legs are x's, then my hypotenuse is going to be that x square root of 2. Okay, let's talk about our 30, 60, 90 triangle. Now that name 30, 60, 90 is really just referring to these angles, but it's just a way to distinguish that this is the triangle we're talking about. Okay, and so we're going to say if we have that 30, 60, 90 triangle, so in a 30, 60, 90 triangle, if the shorter leg, so that smallest side, is x, then the longer leg is x square root of 3, and the hypotenuse is 2x. Okay, and again, that really is just restating everything that we have here in our two diagrams that we came up with. Okay. As far as practice problems for this section, they're fairly straightforward. We really just have to decide what kind of triangle we have, and then what is that x value that we're trying to work with. How do we get that extra piece? Okay, so we're actually going to start with a little bit of a story problem here to work with, which is how far is it from home base to second base, which is really along this dotted line here. So if I'm starting down here at home base and I need to say throw a ball from home to second, how far do I have to throw that ball? Okay, and this is talking baseball. Softballs are similar measurements, but they might be slightly smaller. Okay, so that's what we're going to work with here. So if we look here, I have side lengths labeled on this kind of square here that all of the distances between the bases are 90. So if I want to find that distance straight through the middle, kind of that diagonal of the square, I'm going to look at just one of these triangles. So I'm going to look at kind of this right side here, but I'm going to redraw it. Okay. Now the only reason I'm drawing it this way is so it matches our picture from the top. So I know I have my 90-degree angle. I know that each of my legs here are going to be 90 degrees, And again, I'm trying to find that longest side. For now, I'm just going to call it M. I don't want to use X because I'm going to use X here in just a minute. So I'm just really picking just a random letter. Okay. Now to find this, you could use Pythag. Now the only reason we're not is because we're into the trig section now, and we want to be using our trigonometry. Okay. Pythag is close to trigonometry. We get a version of it, but we want to be using the stuff that we're learning right now. So we're going to do it this way, which is really going back to our isosceles triangle. So if I think here about my isosceles triangle, I'm just going to draw a little version of it down here. I know that my two side lengths were x, and my hypotenuse was x square root of 2. So if I look here, if I'm trying to find x, x is really in the same position as this 90, which means 90 here is x. So if x is 90, I can take that 90 and plug it into the hypotenuse here, and I'll have my answer. So instead of just 90, I'm going to have 90 square root of 2. So right there. Okay. And that really is our answer. Now, that seems like kind of a strange answer just because it's really hard to visualize what 90 times the square root of 2 feet is. And so this is where, if we're being realistic, we should probably round this a little bit just so that we have a ballpark idea of how big this is. So this is our exact measurement, but if I want a ballpark, we can actually multiply 90 times the square root of 2. And if we just do that in our calculator, you should get something about 127.28, and that's in feet. Okay, so it's roughly 127 and a quarter feet from home plate to second base. Okay. Now, let's actually look at number 2. Number 2 is a little bit different here. We want to know the exact value of the side length of a square. So I told you the diagonal here down the middle is 12. I want to know the side length over here on the side. So to do that, again, I'm going to think about this same isosceles triangle that we had. This one's a little bit backwards. It's actually flipped kind of vertically. I'm going to still draw this one that way, just so you can start to see that our pieces still stay in the same spot even when we rotate or flip that triangle around. So my two sides here right now are going to be x, and that's actually what they're labeled. That's what I'm trying to find, so I'm just going to leave it that way. But this side over here is 12. Okay, and you can kind of still see my picture there. Let me move it down. You can see my picture here from that first example. I have my isosceles right triangle, and on that hypotenuse I have x squared root of 2. That's really the same thing as where I have the 12 here, so I'm going to set those equal to each other. I have 12 is equal to x squared root of 2. Let me write that over here a little bit bigger. It's equal to x squared root of 2. So if I want to get x by itself, we can actually divide by 2 here, or sorry, square root of 2, and we get that x is equal to 12 over the square root of 2. And that's our value for that side length, because that's x, and that's what I was trying to find. So that is my answer. Now, here's a little piece that we didn't necessarily talk about before. There's this rule in math, and I would kind of put rules in like quotation marks. It's not really a rule. It's more of just a convention that we've adapted that everyone wants it this way. We don't like square roots in the bottom of fractions. And really this kind of goes back more to ancient times when we didn't have calculators. It's really hard to find what that answer would be with that division of that square root in the bottom. But now that we have calculators, it's really not that big a deal, but I still want to show you this process because it does help us, and it's a good thing to know. So this is the process that we call rationalizing the denominator. And really what it requires is that you know two things. Okay? The first thing is that if I take a number and I multiply it by 1, that doesn't change the value at all. Okay, so I'm going to give you a second to kind of think about that. If I take any number you want, just pick a number, and multiply it by 1, I still get the same number. It doesn't change anything. And that's something you talked about way back in elementary school, junior high. That's something you know. Okay? The other thing you need to know is that when we multiply by that 1, that 1's going to look a little bit different. What it's going to look like is it's always the same thing on top and bottom. So what I need you to realize is that any number divided by itself or set up in a fraction with the same thing on top and bottom is really just 1. It's the same thing as 1. It acts like 1. It just looks different. Okay? And so in order to get this square root out of the bottom, I'm going to multiply by 1, but it's not going to look like 1. It's going to look like that fraction of the same thing on top and bottom. And the piece I'm going to put on top and bottom is really whatever shows up down here in the bottom of the fraction. So in this case, I'm going to use a square root of 2. So I'm going to put a square root of 2 in top and bottom here. And what that does now is when I multiply these together, I'm multiplying straight across, it's going to actually cancel out the square roots in the bottom. So let's see what that does. If I multiply straight across on top, I get 12 square root of 2. And I'm just multiplying those. There's really not anything I can do yet with those. So I'm just going to leave it that way. But on bottom, I'm multiplying the square root of 2 times the square root of 2. So I'm really multiplying a number by itself, and a shorter way to write that is to take the square root of 2 and square it. Well, we know square roots and squares cancel, so those are just going to cancel out, and all I'm left with on the bottom there is a 2. So I have 12 square root of 2 divided by 2. And so now what we can do, because I have numbers outside of this square root, I can actually simplify those. Now I cannot touch the number inside the square root. That square root of 2, it's just stuck. There's nothing I can do there. But I can do 12 divided by 2, which just gives me 6. So this is 6 square root of 2. Okay? So this is actually what our final answer is. This is 6 square root of 2. That's the side length of the square. But it just looks a little nicer. Yes, there's still a square root, but it's at least not in a fraction. We can at least clear up that part of things. Okay? Now, that process is going to get used over the next couple days a couple other times. So you just want to make sure you're familiar with that, and we'll review it as we go through those as well. Okay? Now, if we look at the bottom here, we got one more we need to work with. This one's a little bit more complicated because it's going to use both of our because it's going to use both of our triangles. So if we look here, I actually have kind of on the right side here, I have a 30-degree angle, and on the left side, I have a 45-degree angle. So if I look at this triangle, if I find my missing measure up here at the top, this is going to be 60, okay, which means this whole triangle is a 30, 60, 90 triangle over here on the right side. For this other one, these 45-degree angles actually mean that the two sides across from them, here and here, are going to be the same measure. So this is an isosceles triangle, and again, I have my right angle there in the middle if I need it. Okay? So this is my isosceles right triangle. This is my 30, 60, 90. So we're actually using both of them here. Okay? And what I'm asked to find here is YZ and XZ. So I'm trying to find this side along kind of the edge over here and my entire distance along the bottom. Okay? Now the only side length I'm told to start here is this 8. Okay? Now that 8, if I look at the 30, 60, 90, is the hypotenuse of that triangle. And if I go back up to the top here, the hypotenuse of my 30, 60, 90, that should be 2x. So I'm going to say that 8 here, get back down to the bottom, is going to equal 2x. So in order to get x, I'm just going to simply divide by 2. So x is equal to 4. Now, one of the other sides of my 30, 60, 90 is also 4. I have an x there. It's the side across from the 30. So if I find a 30, go all the way across, that's going to be my middle side here. So x kind of down to whatever this point is at the bottom, that's going to be 4. Okay? So let's go ahead and leave that for now. I need to find this other side of my 30, 60, 90 though. And that's my x square root of 3 side. So my x is 4 and I have the square root of 3. So I'm going to call this 4 square roots of 3. Okay, over here on the other side, because I really need this other portion of this bottom part as well. But if I look, this is our isosceles right triangle. So this side, vertical side, and this horizontal side should be the same. So this is also going to be 4 down there on the bottom. Okay, now we'll come back to what this really is, but if I look here, these are now my two sides. These are like my x's, so x again here is still equal to 4. So this far side, or my hypotenuse of my 30, 60, 90, is going to be 4 square roots of 2, which is really the one side that I want. That's xz. So I'm going to put over here xz is 4 square roots of 2. Then for yz, I need to do a little bit of work, because if I look here, I have it in two portions. I have the 4 and I have the 4 square root of 3. Okay? Now, I get a lot of confusion when we start to try and combine these together. And so I'm going to say ignore this 4 square root of 3 for right now. Say that it's 7. Okay? It's not actually 7, but we can just think of it as 7 right now. Okay? If I was going to take the 7 and the 4 and I want to know that whole side, I'm just going to add them together. So I'm going to do the same thing here. Now, that's a weird number, but I can still just add it together. So I'm going to do 4 plus 4 square root of 3. Okay? And just simply doing that, I can figure out what these are kind of approximately if I want to on my calculator, or I can leave them the way they are. If I found the approximates YZ here, I already did this, was approximately 10.93. Okay, so roughly almost 11. And then 4 square roots of 2, that's 5.66. That's a 5 there. I'm missing 5. Okay? But that's really